Okay, so we're going to start off talking about equilibrium, kind of introducing the equilibrium idea. So we already kind of saw equilibrium a little bit, where I talked about forward and reverse reaction. So we'll just throw up an example. So NO2, O4, kind of turning into 2NO2. So equilibrium is just going to be these reverse arrows, showing your reactions happening in both directions. Where this side is your reaction, and your other side of your product. So equilibrium, we're just looking for kind of seeing a balance between your reactants and your products and the direction of those reactions. If the kind of arrows in two directions is throwing you off, you can always think about it this way. There is one reaction where you have your reactants turning into your products. We'll just say R and B for short. And while this reaction is happening, there's also another one where those products you're making are turning back into reactants. So that's all equilibrium means. What is the balance between these two directions? Reactants going to products and products going back into reactants. So that's the equilibrium idea. Equilibrium is going to be defined by these two things. So if your concentration is going to be consistent, that means your concentration is not changing. However much products you have stays the same. And your reaction rate is equal. So if you have these two things, then we have equilibrium. One of these we're going to talk about a lot. Concentration part, reaction rate, just think about that as how fast the reaction is going. The higher the reaction rate, faster reaction is going to happen. We got to jump into this concentration part because a big part of equilibrium reactions is all about following these concentrations. So we have to talk about what concentrations mean. So when I talk about concentration, you're going to see me use the letter M. So when we talk about concentrations, you can think about like a container. And if I have a certain amount of water, this water would be my solvent. So back in Unit 2, when we talked about liquids, we talked about solutes, solvents, and dissolving. Solvent is whatever you are dissolving things in. So like in this case, my solvent would just be water. And then my solute is just like whatever material I have inside my container. So let's say my solute in this case was like 3 dots. And my solvent was something like 10. Usually we use like milliliters and stuff, but for now we'll just keep the numbers, keep it easy. I would say my concentration is going to be a combination of those two numbers. To be 0.3. And there are different ways that I can change my concentration. So one way I could change it is I could add solute. Right? So if I have the exact same amount of solvent, exact same container, exact same amount, but all I did was I increased my number of dots. Like now I have 10 dots. Well, now my concentration would be 1. Right, so my concentration went from 0.3 to 1. So I'm just increasing my concentration by adding more solute. And solute is anything we care about. So like if we were looking at this equation, my solute would have been that N2O2, or it could have been my NO2. Solute is just whatever chemical we're looking at. Solvent, it's kind of like the liquid that that thing is in. So if you increase solute, you'll increase your concentration. So that would be one way to increase your concentration. Let's say we wanted to do it another way. You could also decrease your solute. So let's say same situation, or decrease your solvent. So same solute, we said in that first situation, it was 3. Same solute, so I'll put 3 dots. But I'm not gonna have as much solvent anymore. Maybe I just have like half as much. Right, so less solvent. Well, then my concentration is also going to. So by decreasing your solvent or decreasing how much water you have, you increase your concentration. So you can think about making like Kool-Aid or lemonade, right? If solvent is like your liquid and solute is like the sugar powder, the less water you have, the sweeter it's going to taste. So that idea of decreasing your solvent, decreasing the water, makes that little bit of sugar you have taste a little bit sweeter. The other way to increase concentration, increase your solute. So same amount of water, but now you dump more of that powder in. That's all concentration is, really this ratio between how much stuff, how much water. And then the way we calculate concentration is we're going to do moles divided by. So this concentration equation is going to pop up a little bit. But again, it's that same ratio. Moles divided by liters. How much stuff do you have? Divided by how much stuff is there in your container. So when this ratio of moles over liters stays consistent on both sides of your equation, that's when we say we've reached equilibrium. That's a little concentration. Okay, so back to the idea of equilibrium. So for equilibrium, we're always looking for kind of the balance to figure out like how much of each side of the reaction do we have. So we're going to have this thing called our equilibrium constant. And we use the letter K for that. So this is an equation we're going to be using a ton for the rest of the school year. Equilibrium, we use that letter K. When we get into acids and bases, those are equilibrium reactions. And you're going to see the same general idea come up. So because we want to keep things pretty general, we're going to use a general formula. So if I want to figure out this ratio, because equilibrium constant, it's really just a ratio. It's a concentration ratio. So we're going to take our products divided by our reactant. So if I know the concentration of my products, or how much product do I have, and I divide that by how many reactants I have, or my concentration of reactants, I'm going to get this ratio that tells me, do I have more products or more reactants? So just a quick little side. Let's say your products was 10, reactants was 1. Well, that ratio would be 10, right? So in this situation, well, your products are dominating this kind of reaction. So like your equilibrium would favor your products. But let's say we flip that. And it was 1/10. Well, now in this case, your reactants are dominating the reaction. There are more reactants in there. There's 10 times as many reactants as products. So that's how we would use that. Just keep in mind, super important, that the numbers we're plugging in here are concentrations. So anytime you see these kind of brackets, just know we're talking about concentration. So brackets equal concentration. So that's like your general equilibrium formula. So let's go ahead and write an example. Using this example I threw up a little bit earlier. If I want to see, I have N2O4 and it's going to break down into 2 NO2s. I'm going to write a little formula for that. So my equilibrium constant for that is going to be your products. So it would be my concentration of NO2. So I want that concentration. And I'm going to divide it by my concentration of N2O4. Now I also need to take into account my stoichiometry. For every 1 NO24 I have, it's going to turn into 2 NO2s. So there's going to be twice as many NO2s present. So what I can do is, because there are 2, I'll do it. Is I'm going to add a second NO2 because I make 2 of those NO2s. So I'll add a second. And what you notice is, if you think back a little bit to math, if I have 2 x variables and I multiply them together, I can just simplify that as x squared. So I want to do the same thing here. I'm going to simplify that. What's that 2? I'm just going to square that. Still divided by N2. So if you see a coefficient in your balance formula, that'll just be like an exponent that we're going to end up throwing in our equilibrium formula. So anytime you see like a little exponent, or anytime you see a coefficient, that's going to become an exponent. So I'm going to write like a general formula that you might see if you kind of watch other review videos, or you kind of look it up online. A lot of the times it'll be written out like this. Where you have some kind of reactant A plus B, and it's going to turn into C plus D. And then you have these coefficients in front. And the way we would write that out is going to be your concentration of C raised to C squared times D raised to D squared over A raised to A, and then B raised to B. So it's going to be that general formula. Again, these coefficients, we're just turning those into exponents. That's all we're doing for these general formulas. So that's how we write equilibrium constants. We're just trying to find a ratio for products over reactants. One important note, when you're writing these, is states of matter matter. So the states of matter that you can use for an equilibrium reaction are going to be liquids, gases, and then aqueous. So those are the only three states of matter that you can use: liquid, gas, and aqueous. You cannot use solids for equilibrium reactions. Because if you think about your precipitation reaction that you were doing during lab, if you make like a solid thing, it's going to stay as that solid thing. It's not going to turn back into a liquid. So last thing we're going to talk about is what these equilibrium constants can tell you. So you have two situations that kind of connect to the ratios I was telling you before. And those are going to be if K is going to be significantly bigger than 1, or if K is going to be significantly smaller. And this will tell you which side of the reaction is going to be favored. I think it's going to be 10. So if your reaction is significantly bigger than 1, so usually you're looking at like numbers like 10 and bigger, you're going to be reactive favored. If your numbers are significantly smaller than 1, so you're looking at like 0.1, then you're going to be product. And again, you can just get that from this kind of setup. It's like if you plugged in numbers and you see that your products are way bigger, it'll tell you kind of what side of the reaction is favored, what direction we're going to be moving in. But from this kind of introduction, big ideas is this equilibrium formula. Just knowing it's going to be concentration of products over reactants. And then knowing that those little subscripts or those coefficients are going to act like exponents. You should know the state of matter rule. Knowing that if you see a solid in your reaction, you just ignore it. You do not include it here. Those are going to be your big takeaways from this little short review video. Okay.